Okay. Okay, so hi, this is Cliff Click. This is Coffee Compiler Club. You're being recorded live. The video shows up on YouTube sometimes a day or two. If you don't like that, bail out now. Anything to do with compilers, code gen, runtime, performance, garbage collection, type systems, I don't know, concurrency, language design, theory, all that kind of stuff. It's all good. I reserve the right to moderate. Mute your mic if you're not actually talking so that we don't get a bunch of background noise. I expect people show up late because I screwed up and sent out the invites late. That's it. We're good to go. We usually run an hour and a half, actually. We usually run an hour and a half. These things run on now. It's all good. Hello. I sometimes start with a progress report on AA. Still working out bugs, still getting it stable, getting further through my tests, progress, slow going.
First step is to admit you have a problem.
Yeah, exactly. Right. Several in this case. A startup banging on my head and you know, Julia startup, I've got them like 40, 50% faster than where they were a month ago. Depends on what benchmark you measure against, and they have a huge amount of performance they've left on the table for, you know, bad data structure choices. So we may, I think we get them another 50% without too much trouble. Like I said, a huge amount of performance left on the table. And then after that, there's like a 10x waiting if they change data structures. And I claim there's probably 50% more if they change from Julia to Java. So those are like big numbers for complete rewrites. And you know, not everyone's excited about the concept of a complete rewrite. So we'll see what they decide to take.
So was it some kind of compiler and language level change, or it is some change in their code data? Okay.
There are several fails with Julia. Like Julia works well if you're writing C/Fortran high performance code. They're writing sort of tricky systemsy code because they're writing a database. And they're thinking big data, but actually they're writing a database. So they have tricky systemsy code, which has a lot of hot path, cold path things and no profile data to LLVM. So LLVM is running around without any profile. Actually, Arthur, you're a good person. How do you get profile data into LLVM?
Well, there is metadata you can attach to instructions, and then everything else should use it pretty straightforwardly.
So the Julia produces LLVM IR. There's some way at the IR level to attach profile data.
Yeah. So basically on branches and things like selects.
Yeah, I don't know anything about LLVM's IR at all. I was looking, there were several fails with LLVM, performance fails. One was the no hot path, cold path splitting, or even whatever, no reasonable inlining, no profile data. In this case, a lot of handwritten inlining on the Julia side that was not profile driven, that led to a lot of like stupidly large functions for no good reason.
Well, the hot and cold splitting, the problem is that you're not feeding the profile. Like once you have profile, it will do this.
Yeah. I have faith that LLVM will get it right if it had profile data. And Julia has no runtime, so it can't hand out profile data. So that's a different discussion.
Where you get it, yeah.
Yeah, it's a different discussion. And the other one was cross JIT boundary calls. Always did a fairly horrific load a large code pointer from a global field memory and into a register and then to a call register.
It has a thunk that it just leaves in place.
Yeah, basically, it's a poor man's linker. Like they didn't even, like a standard linker would have hacked the call instruction to have A call B directly. Instead, you hack the memory
to solve
address.
The linking problem with permanent shared mutable global state.
I'm sorry?
Yes.
They're solving the linker problem with mutable global state.
Yes. It's not really mutable. It's very slowly mutating. It typically goes from unused to used, but you can, on rare occasions, have it switch if you add another lazily add another type profile, and because of Julia's dynamic dispatch, they decide they have to dispatch to a different method.
Right, those dispatches are rare, but it's going to cause optimization
Right,
problems
except in
everywhere
large
always.
complex system code, those dispatches are extremely common, happen all over the place. So they are drowning their branch target buffer to death. So all those branches are unpredicted and they're all over the place. And no profile data to go help them. And they have messed themselves up in a couple other ways too that are unrelated to LLVM, but they show up as being really bad code gen out of LLVM and really bad compile times out of LLVM. So
what do they do for inlining? You said that you don't like what the inliner does. Do they just use the default inliner and have everything in one
use
compiler?
at inline keyword at the Julia level without profiles to back it up. So they're a hodgepodge. Some are in good places, some are in bad places. Some are in core deep inner structures that then get inlined many layers deep, and they were thinking something would get folded away by the compiler that it does not, due to what's in Julia called a type instability, which leads to dynamic dispatch. It's like a static call versus a virtual call. Like the land of Java, virtual calls that actually go megamorphic take this horrible load jump register. But in theory and in practice, they're rare, but not totally rare. Oh, the better answer is the whole thing with like compiling Jython or JRuby or any of those things on the JVM, where you end up using an interface call, Groovy, a billion interface calls to go make a standard. Your normal call becomes an interface call with 20 interfaces to go look up, right? So that's kind of the domain that they're falling into fairly often. It's a different dispatch logic, but it's not the cheap path that you would expect. And that's kind of their common path, is not the cheap path.
But then it sounds like the problem with inlining is problem was the lack of direct calls to inline through. So like if you have
there are several problems here. One of them is they're using at inline inappropriately. Okay. Another one is they have failed to get their types simple enough that Julia's type inferencing can figure it out. Julia has a problem that if you fail to get the inferencing done the right way, they don't declare it a bug, and you have no way to declare it a bug, but instead your code slows down by a factor of 10. Sometimes a factor of 10 can be ignored. Sometimes it's the death knell of the universe and needs to be a bug. So a mystery, slight, modest change to code in some complex, twisty typing logic causing you to go 10x faster, 10x slower is not a good programming model. It's not a performance stable model. Some other guy somewhere else in the program changes some other modest thing. This code over here, unrelated to that code, got 10x slower. It shows up next week when we finally get around to running benchmarks and see that the benchmarks slow down. Now go back in time and figure it out. Okay, this putback did it, but now why? And then it takes the next 2 days to sort out why actually it slowed down by 10x. Multiply that by 50 people on a much larger code base, and they get a continuous series of regressions and performance. The performance is going like this.
Yeah, it's pretty obvious they should rewrite it in Ruby.
Yeah, absolutely. Then it would just suck continuously, and it'd be uniformly bad, and life would be done. So sorry, I've been ranting on these guys, and they're getting a clue finally. But there are a long ways to go, and the major performance gains will become from major rewriting, which they're not typically terribly excited about. So here's Charlie Gracie. He could go defend Ruby or not.
I mean, that's an expensive solution to an expensive problem.
Yes. Yeah, I think that they have funding, but then it's not gonna last forever. So they're trying to decide. I'm telling them, take a year off and rewrite. Okay, that sucks, but you're never going to get 10x any other way. Now, do you want to just live without the 10x? They have some asymptotic improvements over standard database operations. Some things they run asymptotically faster for better algorithms on. That's pretty cool. Some normal everyday operations they run 100 times slower. That kind of sucks. Can we fix the 100x and keep the asymptotic improvement? Yeah. Can we do it in less than a year? Well, can we do it with less than a complete data structure rewrite? Maybe. maybe not, probably not actually. I don't think there's any way to rescue that one right now. So I'm still diving into how bad their data structures are and if there's a solution. But they have chosen.
Is this like the typical, if you stick this thing in an array of structs of arrays, it'll actually perform much better than just your
They
array
have
of structs?
their core concept is a B epsilon tree where they lazily push epsilons, which are deltas to the database. It's a database down into the leaves. And the B's are blocks that go back by like S3 or whatever your cloud-backed storage is. This kind of a solution, for instance, pretty much disallows all parallelism because you have to start the root, work your way down, pushing your epsilons forward, or you have a stale view of the database. So immediately, no parallelism. Well, that kind of sucks. Okay. The next thing is that there's a lot of complexity in how they look at the blocks, and they have further made them type specific to the schema in the database. So every block has a unique, every table has a block which has a unique schema based on the types of the things, whether they're ints or floats or strings or bits or bytes or blobs or whatever, which turns into every time you have anything to do with any new database structure, all the code gets rejitted from scratch by LLVM, and that leads to this horrific startup time problem they have. Whereas if I go to look at H2O, there are a dozen underlying data types, which are the compressed versions of whatever you started from, and there's no more than a dozen, and they're all pre-cooked, and they showed up as soon as you got things jitted the one time, not hundreds and actually thousands for them, but a dozen. So, and then it covers all your database needs in terms of all your data access needs. It's a giant multi-terabyte vector that's distributed in parallel and scale out and has extremely low latency because it's all compressed to hell and gone. And so it runs through your memory bandwidth hierarchy, low latency and all that kind of shit. And they are far, far removed from that. The next thing they do is their cool algorithm, which is asymptotically better, is implemented in a way which is sort of huge constant time overheads for no good reason. They're slopping around arrays of solutions sort of left and right, and then they're filling in solution pieces as they walk through the data, but they copy an array which represents basically an entire database row as they're walking through their solution. But they copy it at every minor step. As opposed to just having an array that you bump the field pieces in and out as you walk forward. And as a consequence, to walk one row of the database to the next row to just do a quick test, get a value and decide it wins or loses and go to the next value requires copying 100 bytes to a kilobyte, depending on the size of your query or the size of your database row, some blending of the two. So they pick up a 1,000-fold slowdown right there, 100-fold to 1,000. So just
is this a SQL database?
Oh, no. This is, they have a custom different data language, different concept, but it's relational, like SQL's relational, but they are all about the relations directly. And this lets them express some problems in a much more natural way than SQL does. And it leads to this asymptotic speed up when they can sort a problem in a better way. And their implementation strategy is just, like I said, it's got a 1,000-fold slowdown for no good reason. So I think we can speed them up by a lot, but there's a major data structure implementation, and then keep their goodness too. So their goal is to go attack the SQL market. And these are guys that have been, the founder has been out of many large startups with high value successful exits. So this is a guy who's won a lot, and he is charging head forward into the Oracle monster and he's sharpening his spear and preparing to do battle. And he's had a lot of wins under his belt. So there's a big dinosaur.
From the 1-minute description, it sounds to me like they'd be better off in a log structured merge tree than a B tree.
No, I'd go to H2O style. Just my old sort of H2O. Constant factors drop to nanosecond per element, literally nanosecond per element. Like I truly get memory bandwidth speeds across all your data. So you got a terabyte data set divided by 50 gigs a second memory bandwidth, and a dozen nodes, and that terabyte gets chomped down in a second. And I have seen that reliably, repeatably done over and over. So I would start from that base and see if there's an asymptotic improvement game to be played. As soon as you said log merge tree, I'm asking how you do concurrent distributed. Right, that's you give up on parallelism. You know, every machine these days is, I guess, I'm maybe on the low end now. I only got like 20, you know, 10 cores to 20 hyperthread. I don't know, I'm being on the low end. You go to pizza box in the data center, I'd expect you to get 32 without any trouble at all. You get 128 with trying a little bit. But if you're looking for low cost Amazon, grab your instances, you probably want more memory and more cores for more efficiency, and still not too expensive.
So you described how Julia has this like global set of pointers that basically allows you to define a new class at runtime and rebuild structures.
Yeah, they
The
are.
JVM clearly also, I can throw new classes at it. It's a very open world. How do you stop a new class appears from basically having to do a garbage collection style, stop the entire world, go find out every assumption that got invalidated and clean things up?
Well, that's what Hotspot's been doing for 25 years.
Did the Azul boxes do the same thing? If I take in a new class, go stop the world and figure out what I broke?
It will go find out what you broke, but it will not necessarily stop the world. So you said stop the world. What really happens is that there is a point in time, there's a linearization point where the class is exposed. Up until that point, the class is not exposed, and in the background, we can go do all kinds of fun things, like look at what that class is trying to touch. And we go to an internally maintained set of Hotspot VM, basically database, not a database in any way, it's just a collection of facts that lists who depends on what not having or having which kind of subclassing. So you want to inject a new subclass. We're going to go lock down, so stop, but not the world, stop the ability to implement, to inject new classes. And you will make an atomic walk inside and also stop the ability to inject new code. And you will make an atomic walk to decide which piece of code will get blown out by this. And then you'll flip the bit saying these pieces are going to be dead, and then I'm in. And then you release your big lock, and the compiler has to recheck to see if he got blown out in the interim, and other classes can now try to play the same game or whatever. But it's not stopping everyone else. It just stops class injection and code injection until you validate your current assumptions in the current code base.
And you would use the same save points that we're using for like GC, or is that a different save point concept for when a class can get swapped out?
So break out the pieces here. The save points that get used for GC are in fact run together, but they could be separate semantically. In practice, they're run together, fine. The save point mechanism you're talking about is not in any way related to what I just said. What I said was somebody's loading a class. They have stopped at a save point. Everyone else is just running willy-nilly. We lock a database against changes. We confirm which pieces of code get blown out by this new class getting loaded. Then we'll flip the bit saying there's another step I didn't say because I was trying to keep it a little simpler, but a little more complicated here. But we'll flip the bit saying I added the subclass. We then go take the list of methods that are now broken, and we hammer them in a way that prevents the brokenness from being exposed. And that varies in two major techniques. One is you cannot call this method ever again. So there is a one-time patch at the head of the method saying, if you get here, go into the runtime and figure out what the hell to do next. There's another one that says that
so this is the I'm dead, go deop, please.
Yeah, but you're at a method head, so it's not really even a deop. You just have to flip to the interpreter at a method call boundary. So it's actually, with no stack repacking is done. Or it's the minimal, it's the one frame you wrote for the compiled JIT code gets flipped to the interpreter frame. You're off into the interpreter, except that we actually do the lookup and see if there is already a replacement, and maybe you just flip to the replacement right away and you have a stale prediction and an inline cache, and we update the inline cache, and there's a bunch of corner cases that I'm whipping through here. And the other major one is exactly the deopt one, but that's one that says I've called in, and then I called out, went further downhill, down into a deeper stack. And I'm way deep in some way deep stack, and then somebody tries to blow out the method on my stack that I have to unwind to get to. And so at that point, I have to modify my stack. So when I would return to this method's frame here, so stack going down, I would unwind, return to this method frame, then continue execution. I cannot continue execution. I patch my stack, and that is done at a ragged checkpoint mechanism. So it's not a true safe point. It's every thread does it their own way, and they crawl their own stack and patch as needed. And then when I do in fact unwind and get here, the return will take me off to a deop stub, which will then look at this stack frame and repack it as a deopt, and off into the interpreter you go, and you figure it out from there. So safe points show up, but not in a stop the world context, only in the context of if you are running this code and it's on your stack, you need to patch it so that you don't fall into it accidentally and continue execution. Does that make sense?
It does, and it sounds like you can actually hot swap code without losing performance for
exactly. That was the whole point. No one else is actually stopped. People who are stopped get stopped for the cost of an L1 hot in your L1 cache personal stack crawl, which is typically a handful of microseconds. Depends how many. It really depends on how many cache misses you get looking at metadata, but most of the stuff's sort of pre-cooked nicely, and you're done in high nanos, modest micros, and then you're off and away again. This is independent, of course, of jitting overheads. If you actually need them code, and now it has to get rejitted, and then you're off in the interpreter waiting for the JIT to get done and whatever. That's a different overhead. But the act of loading a class does not cause any sort of stop the world beatdown situation. Yeah, that's fine. I did a lot of that stuff, and I redid it at Azul. Crazy ass things. And I tried to talk to the JavaScript guys and how doing it too, and they bailed out and took an easier answer.
Sounds like you're gonna have to redo the same thing for LLVM at some point.
Maybe. That's on the cards. I know what to do now. It's a lot simpler.
Well, but it's not quite LLVM. Like LLVM as a compiler, and what we are talking about is runtime.
It's a runtime. Yeah, it's not right. It's not LLVM. It's a runtime. Generically, a runtime for anybody's backend. What backend? I don't care. The backend, I said runtime. The runtime supports loading new code, new classes, new compilations, supports profiling, supports garbage collection, supports stopping threads in bulk and singleton with nanosecond latency typical to stop a thread, and have it do some self-service task and then start again and shit like that. That kind of a runtime, Java's had forever and a day, and it has a high payoff, and people don't think about it, but that's the core guts that make everything else go.
And you said that JavaScript doesn't do things like that?
No, they take an indirection call. Because they didn't want to deal with, one of the mystery bug deaths you get is you have an inline cache-like effect where you've made a comparison check to a class, and you've got a correct answer, and you make a call instruction, and then the OS swaps you out, and the x86 push you to sleep for a decade, and then you woke up with a bad prediction, having passed a correct prediction, literally from your thread's point of view, the clock cycle before, but in reality, a month, a year, centuries have passed, and it's all different now, and you jump to some piece of code. Okay, when can you delete the piece of code you're jumping to? Well, it turns out you cannot delete it until you pass that thread through a safe point and validate it doesn't have a bad prediction waiting, pending as a preemptive OS going to get restarted any second and go. So you can't get rid of dead code. You can't get rid of broken code because somebody's going to jump to it until everyone's gone through a safe point.
Isn't the problem that the prediction changes at not at a safe point?
That's correct. That's part of the problem. Yes, the predictions clearly are high performance. This is inline cache behaviors. What do you want to do here? Changing the prediction at a safe point is way too expensive because you'll have an infinite number of prediction changes. You generate bazillions of these inline caches. You can't stop everybody every time you want to change one. Many of them never get a prediction because they never get hit, but they get generated.
Wait, probably I don't understand the issue. So we have a check on the type, and if we successfully predicted the type, we have a direct call to the target method of this receiver.
So the test is compare jump not equal to fail, call predicted. So you can do the compare, and it's correct, get flipped out by the OS. Some future time later, you come back in, you have a call to a target. Meanwhile, a new subclass has got loaded, and the prediction's incorrect.
Wait, but your receiver is still the same object, or they have a way to replace the
code you generated. Your target code is different. Your receiver didn't change, so the abstract method you would call has not changed. But the code that got generated for the original call included a subclass, included references to the subclass that got modified, and is now incorrect. That code is broken. You cannot call that code.
Okay, but then probably you protect yourself by making the old version non-entrant, and you would stop doing this.
Yes, you make the old version not entrant. Now, when can you get rid of a non-entrant version?
That's the cleanup.
What is the lifetime of that code? It really sucks to track all the lifetime issues. And if you fail to get it right, some poor slob once in a blue moon takes a misprediction to a piece of code you reclaimed and crashes and burns. And the scale of Java, that would happen actually quite frequently, because back in the day, we traced down one of these things. It took a fucking year to go diagnose and debug. The lifetime, I have a talk on this that I rarely give because no one ever gets far enough along in implementation strategies to figure out it's an issue. But I have a really deep, in-depth, horrific talk explaining why you do the following lifecycle things and when you can get rid of.
It's basically MVCC for code.
Yeah.
Until everyone passes a tick, which you're calling a safe point.
Yeah.
Exactly. You can't replace or remove anything.
Yes.
So code is additive only.
That is a better answer than what I came up with. I worked my way through, now that you've said that, something that more or less behaves very similar to MVCC. Yeah.
Yeah, and it's also
your
very
problem there is just that you're not writing your runtime in a garbage collected language.
Your runtime cannot be garbage collected because you're implementing the garbage collector. The meta-ness has to stop somewhere. It ain't turtles all the way down.
But it is similar to the challenges that you would have with a concurrent GC. It's a similar challenge, which is until you've all gone through a certain phase of the process, no one can go to the next phase.
Yeah, one of the fails and successes here was that with the concurrent GC, we knew that up front. And so you planned it in the design. And in the case of hotspot in the code, it was not known up front. It was not planned in the design. It was horrifically found out later. Some of the work done at Azul was exactly to move the code fields into the GC. So there's a wrapper around. Basically, you can think of it as a finalizer wrapper around the code blobs. So the garbage collector, in fact, tracks the lifetime for a lot of these things now. Not everything, but a fair amount. That was making life simpler. The hotspot, as done by like OpenJDK, still does it the horrific way. I think the is much better.
Although I think I might be lost again. So I understand the problem with the fact that we cannot clean up because there might be a stale reference to a code blob which is not entrant. Yeah. But how is it solved in hotspot then?
Once a thread goes through a safe point, you throw a flag on the thread safe point saying self-service task. One of the self-service tasks is I passed this safe point. That's all it does. But that meant that you no longer were in the middle of a prior prediction.
Okay, and you can clean up your caches.
Yes. So once you pass that, you just flipped the bit. Somebody else is watching the threads, and when the last thread flips his bit saying I've passed the safe point, then you can argue you're in a new generation or a new era, if you will, and no one's holding on to a stale prediction in their execution pipeline of their CPU. Now their iCaches have these predictions. You have to blow their iCaches out, and you have to blow their Dcaches out, and all this kind of stuff. x86 makes no promises about iCache to Dcache coherency, so you have to blow them both. That has a performance hit, but you don't typically need to take that one except on the thread doing the patching. I think actually we don't blow them out. When do we blow out iCaches? We might force iCaches. I'll have to look at the Azul code. I think we might force iCaches on a change of target method. Because
Part of that comes
managing
down
the
to just
Dcache
what
doesn't
is
do
the
it.
memory model of the code segments that you have.
Well, it's an x86. So, I'm sorry, ask again?
So like in the Java memory model, you can sort of be stale for a while on your thread because
Yeah, okay, yeah, back up.
you're just reading before and it was a data race
Right,
anyway.
back up,
It
back up.
almost feels like each time you add a new class, you've created a kind of
Right.
data race.
Stop. So the first thing you said was in the Java memory model, fail. We're doing an x86 or an ARM or SunSpark or a Titanium. We're not doing a Java memory model. Every piece of hardware has a different memory model. We're doing coherency on pieces of hardware. We will implement the Java memory model in how we generate the code, but we're talking about the code itself right now. So this code does not get to rely on the Java memory model.
That makes sense.
Okay, so the x86 model is typically more conservative than the Java memory model, except where it's not. And it's specifically not on iCache coherency. So if you patch an inline cache, your iCache will never ever see that patch unless you whack it on the head. You flush the iCache. Right, or it randomly gets flushed at some future date and you happen to see at that point. So you can't live in that state forever. But the processor can totally live in a broken state, an coherent state between code and iCache indefinitely. So you have to force it.
You can force it from the writing thread, or you have to force it from the reading thread.
You have to force it from the reading thread.
That's what I thought.
Which is the Safepoint hack. So the guy walking the Safepoint that says your iCache holds onto a stale prediction.
Can I ask a out of order question here? Speaking of x86, but doesn't that mean that you can't rewrite the preamble for a function without the reader going through a Safepoint?
You can rewrite it. The reader may just ignore you until.
Well, what if it crosses a paragraph boundary? Then it may pick up part of it and not the other part.
No, exactly.
No?
So excellent. The rules is that all code which can be patched has to not span a cache line boundary with a partial instruction, except under very carefully diagnosed circumstances, defined circumstances. So there is a set of self-modifying code templates we built in Hotspot. Those templates had marker points where a cache line boundary was allowed and places where it was not. And we inserted no ops as needed to avoid spanning cache line in a bad place. So an inline cache, so somebody put out a Twitter feed limit or a page on inline cache something, or an inline cache in reality in Hotspot has a number of parts, set of instructions, depends on code entry versus inline cache directly or whatever, self-modifying piece of code. They have delineations where cache line boundaries can occur. They have offsets according to how many nops you inserted that are tracked with that cache line that gets patched individually. There's a record of an inline cache started here, and then there was some way you could look at it and know where the nops went when came time to go patch it. And those are all sort of very carefully defined. So the standard one inline cache would be load a constant, which you're going to patch the constant. So there's 1 or 2 bytes for the load and a 4-byte constant. Then there's a jump and an offset, and the offset's typically forced small, but you can patch the offset, unfortunately, and sometimes you had to have it a big offset, so there were some games there. And then you had a call, which is 1 byte always, and a 4-byte offset, which you were going to patch. So you couldn't patch the middle of the constant, the middle of the jump offset, and the call. Everyone else can be on different cache line boundaries, and therefore running processors might see patches out of order. So for instance, if I wanted to change the jump to a jump always fail, and I wanted to change the call to being something unrelated because I didn't care because the jump always fail was covering me, and I did them in order, that wasn't good enough. Because the jump may appear out of order relative to the patch on the call unless I just flushed everyone's iCache. But I had no atomicity. If there was a cache line boundary there, I had no atomicity between those two. So we always had to be able to patch each of the 3 parts in an inline cache where anybody could see any part in any order. So what we typically did was we kept a call at a fail, and we patched the load and the jump, and then we forced an iCache flush.
So theoretically, you could patch in a different place, build your patches first, and then simply replace the entry into the function with an unconditional jump to the patch, and then you don't care. Then you don't care if they pick it up before the next one or not.
If you could atomically patch the unconditional, yes, that sorts one. That's what we call the non-entrant patch. We do that. That's the not-entrant patch. We make a method not entrant by jamming down atomically, and usually methods are forced to start at an iCache boundary anyhow because of performance. So you have a free, I just slapped a word
or at
down.
least a paragraph boundary, or yeah,
whatever an iCache boundary would be. I don't, when you say paragraph, I don't know what that means. So I'm talking cache lines. It's fine, right? And the TLB boundaries matter too in some of these cases also.
So when I say paragraph, I just mean something that's big enough that I can put an unconditional jump and a 4-byte pointer into. So 16 bytes would be a fine paragraph.
Yeah, exactly. Right.
Because it's also because a cache line is subdividable by a paragraph.
Okay.
Evenly divisible.
Yeah.
Evenly divisible by a paragraph.
Okay.
I don't know. We used to call them paragraphs back in the 1940s. What do you want me to tell you?
It is fine. But a not-entrant is exactly that. We patch the head of the method with a jump to somewhere else. And the somewhere else does all kinds of shenanigans. Usually it squirrels your stack away a little bit safer, and then it jumps into the C code, and then the C starts to sort out what happened and where to go next. Because sometimes you have the correct target method pre-compiled and you're ready to go. Sometimes you need to repack the stack for the interpreter, and you jump to a little stub that says repack for the interpreter, and then jump to the interpreter, and he takes off and goes and whatever. It's a little simpler than the deopt thing. Fine. So yes, so that was one of the patchable points. There was a third patchable point. I'm trying to remember now what the third one was. There was another technology we used. Oh, okay. Here's the one we used to avoid having to flush remotely. When you had a return into some piece of code, we would fill the body of the method with no ops. It was an odd thing to do, but if you had no atomic boundary after a certain point, you could get away with partially seeing nops and partially not. There was something we did to avoid that though, Arthur. I'm trying to remember what the hell we did there. We would slam a method with nops. So any return into it would hit the nops and fall off the bottom where you had a jump to save you. But you could see half of a nop and half of a damaged instruction. And I know we fixed that, and I'm trying to remember how the hell we did that.
Well, we recently introduced an alternative way to deopt, and I think we're going to switch to it because this way you will. So this way you make the code blob non-reusable. But we have scenarios where we want to deopt the frame, but the code blob is fine. And I think the trigger for that was there was a customer who was complaining that our Stack Overflow exception is propagated too slowly, because propagating Stack Overflow, we would deopt the code blob because, like, yeah, nobody thought the Stack Overflow exception needs to be fast, like,
right,
correctness. But no, they had some kind of language, and their customers would write rules in it, and instead of recognizing infinite recursion, they would catch Stack Overflow exception and then report an error to the user. Anyways, that was the first scenario. Well, okay, we want to deopt the frame.
So wait, just a second, Arthur. Make sure I understand this correctly. So instead of using goto, they threw an exception. Okay, got it. Yep.
Exactly. Yeah, Arthur. Yeah, Arthur. Trolls has some comment in the chat that's basically the same thing. Yeah, exactly. Yeah. Exactly.
Yeah,
so what is the big O of a Stack Overflow?
Well, and then yeah, I think they compared this to what OpenJDK does, and OpenJDK doesn't use this knopping scheme. They can deopt the frame, and then they were saying, well, you are slow. OpenJDK does it much faster. So can you do something about it? And then there are other cases. For example, we can speculate that a call never throws an exception, and
Right.
if a throw happens, we can't deopt the frame. Like the code blob is fine. But we can deopt the frame, resume in the interpreter, go to the handler, and
No,
re-enter.
what was in there now could totally do that. The deop was independent of, the repack the stack was independent of trashing a frame, trashing a code blob, sorry. Trashing a code blob was done when the code was not usable again.
Yeah, but the way it was implemented by filling the knobs into the code blob.
No, that was done when we decided the code blob was not usable again. Independently, there was a deop the frame, which was not wiping the code blob out.
Well, at the point like 1 year ago, the only mechanism there was wiping the code blob with knobs and deopting this way. Like maybe it was lost.
Yeah, because it was they were independent and completely one. You do whatever you want. Like I swear I did this for like throwing exceptions. You know, speaking of Stack Overflows, you can throw a Stack Overflow exception cross threads. One thread can throw a Stack Overflow on another thread, or a null pointer that can't possibly happen, or any exception you want. And that's a point where the receiver takes an exception, takes a safe point check, checks the safe point. The safe point claims he's getting an exception installed on him against his will. He installs the exception. That's typically requires him to start the stack unwind process to get a catch. Yeah, Stack Overflows are not a reasonable message passing mechanism, and they're not fast enough.
Well, we made them faster.
So I claim there's a way
they
that
should have used out of memory error.
There's a cross thread.
They should have used out of memory error rather than Stack Overflow.
Exactly.
It would have been better.
Exactly.
Or you have them both, and it's a more complicated protocol.
Yeah, there you go. You have 2 bits.
They could even just put a counter in and say that we give up if you go more than 10,000 deep, and then you know.
Now, Arthur and Cliff, when you deopt, there are cases where you actually have to expand the frames, and there are cases where you have to contract the frames as a side effect of deopt.
Yeah.
Do you create a fake function to do that, so you can then return to the wrong point on the stack? What's the rewrite?
Almost. So the first thing you do is you don't rewrite the frame until you've unwound all prior frames. So you have an open-ended piece of the stack to go into. And then there are actually 2 rewrites going on here. One of them is manually by the VM, and that one just one thread, another thread has stopped, and this thread just repacks that guy behind his back and doesn't let him go again, right?
Right.
And the other one is one thread does it to himself, and there, yeah, we do a signature to signature. We have a signature cache, we call it. It takes 2 signatures, turns those into register layouts in and out, and does a mapping between them, and then takes whatever jump you want at the end. So you hand it a go to here when you're done, and repack your stack and go to here when you're done. So the usual go to here is you're jumping to either the interpreted to JIT-ed or JIT-ed to interpreted, and you have the style, which is either interpreted, Java JIT-ed, or native, and you have the signature, and you have the output of the other flavor of the same thing. Pick whatever you want, and then he does the mapping, and then and puts it in a cache. And the cache is a very high hit ratio. You get a few hundred in the start of the system, and a few thousand over the lifetime of a very large, busy web server. So it hits really quick, and you have all the signatures you ever screw around with cached. And so now when it happens, you look in the cache, you get a hit. There's some piece of code that's 10, 100 instructions long that ends in a jump, and it just shuffles the stack, and away you go.
Now, within a compiled function, are the Java registers, stack minus constant? What's the, are they actually laid out in the stack frame?
Yeah. No, the Java, you mean like the Java
The
version?
Java, is the Java stack on the x86 stack?
When you're doing the
Sorry,
interpreter,
are the Java registers on the x86 stack?
when you're doing the interpreter, yes. When you're doing JITted code, they're thrown at the optimizer who splatters them on the wall like spaghetti, and
Registers versus,
yeah, wherever it lands, it lands. The typical story is a bunch of those values are unused except on exception paths. So rapidly they get spilled to some slot in memory, and that's where they live the entire function because you never took the exception. But they're available to be either computed or pulled out from some slot in memory, but they're not living in a register per se, and they don't have any other lifetime. This is all called the debug info. Like if you look at a call instruction, which in C2, which subclasses from Safepoints, so the generic Safepoint instruction, it has a whole ton of inputs to it as a node in the graph. And a whole ton of inputs is your entire inline state of every Java virtual machine architected value. So they're all forced to be live inputs to a Safepoint call, if you will. With very low, and Safepoint itself is implemented as a very low frequency branch to some off function call into the VM. So the register allocator knows the branch is very infrequent. It's whenever GC happens to hit the Safepoint. So he's happily to do register allocation such that all of those values that are the live things are off in a low frequency use. That's their only use. So he promptly is strongly encouraged to spill the hell out of them. But the optimizer can optimize them away he likes. And so he might discover there are lots of zero things, or this is equal to that. So they can all share or whatever. He might have, a lot of them might be shared and yada, yada, or constant or whatever. So when it comes down to the actual code gen for the Safepoint off branch, things that are exciting and different have been spilled to the stack or in registers or whatever. Things that are very static are just annotated as, and this is a zero now, and that gets written out so that the code generated doesn't include necessarily stuff a zero in and spill it. The code generated is what we actually had to have to keep what's currently live that wasn't constant and wasn't something else or equal or whatever. And there's some debug info associated with that location that said, and the following values are known to be 0 or 1 or whatever they are.
Yeah, it can go as far as we can replace new allocations, unescaped allocations, with symbolic description, how to recreate the allocation, how to initialize the fields, like how to do an array copy from some other memory location. And this way you don't need to produce this value in the compiled code if it's only used on the deop path.
That was done after I left. It sounds good. It's the right thing to do. Yeah, like there's all these magic tricks, and they're all they let you run faster code.
what's this link, Jin?
GitHub packed ROPC. What's an ROP compiler?
Is it return-oriented programming that the attackers use
God.
to jump to places that were never actually meant to be receivers of function calls?
No, Peter was just here a minute ago. I don't see him now. But he's been in and out, not paying attention.
Hello?
Emulating x86 from OCaml is very slow.
Yes, actually, ROP is what you said, Aaron. And I'm saying that, some people just make use of this trick to, execute the turning completeness programs, So like a couple years ago, some hackers compromised the PlayStation 4 using this kind of technique. It's very interesting. And the basic idea is just like Aaron said. So they make use of the chain of return address to execute programs.
Yeah.
Which is similar to the Stack Overflow things, I think.
It has some similar. Yeah, it has some similarities. Yeah. It's ugly. It's not, x86 is not very performant in that model. Yeah. But, whatever. Stack Overflow for hacking. Can't find Peter? He's not with Matthew?
No.
He's not outside?
Did you let him outside?
In and out, in and out, in and out. I didn't track the parity. my antique cat had yet another stroke. So he's down like 4 lives in the last 2 months. He's forgetful. He walks up to the back door, scratches go out, open the door. He looks confused, walks away, walks back up. 5 minutes later, scratches go out, looks confused, goes out, goes in. He still seems to be enjoying life. So it's not time, but it's getting there. It's going to happen. It's a beloved family pet that's very, very old. All right, enough of that.
The cat is on the roof.
If he gets on the roof, I'd be very happy because it means, he's picked up.
Sorry, it's an old joke.
Yeah.
I'll tell it some other time.
Okay, fine. Yeah, I had a cat who could make to the roof in one jump from the ground floor. That was, an 8-foot vertical leap from a house cat, big house cat, but nonetheless. No fence was going to stop this boy. Okay, what else? Deopt hacks, high performance, blah, 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 injecting code into running things, how to handle.
How portable is the concept itself? I'm just thinking like.
Port it to a dozen different pieces of hardware.
No, I meant portable in the sense of like, isn't this like something that every runtime language would need? Like,
yeah. The theory that this other startup wants me to make Julia go faster is operating from is I can give them the performance you get out of Java, for which I'm going to say, yeah, and have to have a runtime like you get out of Java. And that's going to require a new runtime for Julia. So that's sort of on the table while we're negotiating. Do I want to do that? And will you pay enough? And all that kind of shit. It'd be an open source. If you hear about it, I'll let you know and you'll know, okay, I'm starting an open source project to replumb Julia's backend. Some portion of Julia's performance issues have to do with type inferencing, and a big chunk of them have to do with LLVM being used in the style for which it's not kind of intended. Like this isn't really LLVM to blame here. This is Julia doing systemd programming language without having a systemd runtime under the hood. They had some other issues with Julia and type blowout. So saying the type blowout turning into code blowout on LLVM side, I think. I'm not certain if that can be fixed at the Julia level, or I have to tell these guys to quit making up new types every time the data structure schema picks up a new type. Or every query has a new schema and the query generates new code that has rejet everything from scratch. And it's just like, it's too abysmal. Fine.
Oh, I have a question about different languages based on the LLVM. Just like you mentioned, Julia, I found that Rust is now also based on the LLVM. It sounds like LLVM is like a vehicle of compiler. So, but my question is this an effective way to get like a better compiler? Because, in my understanding, if you want to optimize your code, you have to do it from the higher to the bottom, from the, from the top to the bottom. You have to do some kind of monolithic design, from your programming language to the code generation. So, but the thing is, I feel that many new programmers try to treat LLVM as a vehicle. So, but like Rust, recently I found that Rust literally translates their programs to AST and then translate to a very high level MIR. And after do some kind of language specific optimization, they just lower to LLVM, and it fully depends on the passes of LLVM. And yes, I understand that that is the easy way to get like a decent compiler. But do you think they can beat the real performance by designed by the a dedicated compiler like Golang use like a independent design and
so the performance thing that I thought I heard you say was you'd start from the high and go down.
yes,
At the high level, algorithm changes win all. And it doesn't matter what you're implementing in Go or LLVM or Rust. If you asymptotically better algorithm, that's just
or Visual Basic.
Yeah. After that, my opinion or observation is it's good data structure choices beats everything else. It's because it's all about cache line misses these days. So good data structure choices turn into everything is quick and easy to get out and modify and fits in your caches and yada, 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 whatever. And this is like a sort of a high order bit for everything else that follows. Then the runtime the hotspot uses enables all kinds of jitting things that are roughly similar to what LLVM does. And a little better targeted on the hotspot side to the twisty Java logic code, and LLVM is a little better targeted to Fortran style, big array, big maths kinds of things. But those numbers typically translate to like 20 to 50% speed ups, except occasionally you get these giant speed ups where you hit something like tiling a matrix multiply, which Java does not do. Tiling for registers and memory hierarchy will get you like 10x or better for a matrix multiply. It's a very specific thing. On the Java side, knowing that you have some classes loaded and others lets you take a virtual call into a static call into an inline thing. And again, you can get 10x speedups where a C compiler cannot discover that something will never ever be called or is callable or is not being callable in the current execution. So outside of sort of targeted things, which are important, I admit, the core guts that everyone's sharing here, a better runtime is 50% of what you can get out of a standard optimizing compiler. And then I claim the optimizations done by the hotspot JIT are fairly standardly done by LLVM as well. So those two are roughly comparable, except that the hotspot JIT is like 10x faster to generate the code at that level. So it's faster to generate. There's another 50% if you're into the Java side of things that are specific that Arthur's been working through to make it work for LLVM, like hauling profile data forward, for instance.
Okay, I got it. So you are saying that the performance depends on the compiler and the runtime.
And algorithm. So start from your algorithm.
I believe LLVM smartly choose the correct data structure and algorithm.
LLVM has nothing to do with picking. Oh, I'm sorry. Say again. Would you say LLVM has nothing to do with picking the algorithm? You pick the algorithm, not LLVM.
Yeah, I see. I understand that. But back to my question. So let's see that like a backup like 2 decades. So I'm the guy who decided to write a Java JIT compiler for Java. So I have 2 choices, right? I can make it alone from scratch, or I can make use LLVM or GCC.
You asking me why I chose to from scratch versus LLVM 20 years ago? That's an easy, direct answer. Is that the question? The answer was LLVM couldn't do it 20 years ago. They totally lack no other compiler. Excuse me. No other compiler, and I looked pretty hard, had support for garbage collection, pointer tracking that you could do movable GC, for being able to deopt and reopt for the Java memory model, because as a minimum, the register allocator would dishonor all loads and store behaviors in an effort to do better register allocation, which would immediately defeat the memory model kind of thing. So to get a functioning thing that implemented the Java spec, LLVM and GCC and several other things I looked at were never, ever going to work, or not ever, ever. They were not going to work by an amount amounting to sort of rewriting the compiler from scratch or waiting 20 years for it to catch up. Now, LLVM's caught up in 20 years. Okay, it has. Okay. But 20 years ago, rewriting LLVM to make it support garbage collected pointers, Java memory model, there was 2 or 3 other things it sorted out. Yeah, LLVM was in the discussion. So I see what you said there, Trolls, but I totally talked to the guy I came out of Rice University and we were having heavy discussions with, LLVM was around, but maybe not out of the university yet at that time. I totally talked to, like my advisor was good buddies with Vikram Adve, and who I talked to about the status of LLVM. And that was tossed out as we could do it this way more than 20 years ago.
Yeah, yes, I got it. I think my question is answered. I feel that sometimes I have like 2 choices. One, I can build up a compiler from scratch, or I can make use of existing infrastructure to get this thing done more quickly. I feel that I can, if I do it from scratch, maybe I have much bigger design room to tailor this problem. But from your answer, I feel that LLVM, LLVM is not bad naturally, because so you need to choose like a correct data structure to design a better, smarter algorithm, and you make use of LLVM to implement them. And the other side is runtime.
There's no correlation there. You pick a better algorithm, then once you.
I don't think Jin got your point. So Jin, just to back up, when he says algorithm, he means in the app is using an algorithm, not the compiler, not the native code, but the app itself chooses some algorithm.
Oh, you mean that algorithm compiler doesn't matter? You mean compiler?
So pretend we're using VB, Visual Basic, right? It's an interpreter on Windows, right? Like, so we're using Visual Basic. The most important thing for performance is to use the right algorithm on top of the right data structure in the application. And that beats anything you can do with a compiler.
Oh, yes.
Because if you have big O end of the fourth, like my n log n in VB will kick ass over your end of the fourth in assembly.
And this is why people choose shit like Python, which is interpreted, but it's easy to code and they can get their algorithm right. Having got their algorithm right, they get an asymptotic speed up, and that beats all. Once that's not good enough, now maybe you want to change language where you can compile the code and get another factor X out, right?
Oh, I see.
But I'd say, and maybe Matt can weigh in on this as well from the LLVM futures point of view, but the reason to pick LLVM isn't because of what it already does. It's because of what it's likely to do. Or Artur, you may have an opinion on this as well. So it's like, so for example, why did we pick Java in '96? Well, because we wanted to be able to support not just the 2 or 3 platforms that Java could support at the time, but the 20 platforms that we expected it to support 5 years later. And while we could do a cross compiler between, Linux and Windows x86 and Solaris on x86, it was rather difficult for us to imagine doing a cross compiler to anything else like, Solaris Spark or Mac 68000. Isn't that what it was at the time? 68,000, or was it PowerPC?
Yeah. I like 68,000 as a JIT.
Yeah, well, it was a beautiful assembly. It's the last good-looking assembly language I've ever seen.
Yeah. I guess that's spot on.
I would argue that assembly language these days shouldn't be pretty. They should be good JIT targets.
When I joined Azul as one of the very early employees, they had intentions to do hardware, custom hardware, okay. And they had all kind of crazy ass things to go make Java run faster. And I told them exactly that. No, give me a good JIT target. All other problems have been sorted out. Give me a good JIT target.
Well, I will add to the discussion.
Made very easy to read. So there's not a readability issue there either.
To this discussion on like if you were to write a new compiler, what would you do? I think if you compare like the situation 20 years ago with now, one of the differences, there has been 20 years of evolution in both hotspots and LLVM. And if you got to write something from scratch, now you need to replicate this path. And one of the ways you take something existing, like there's LLVM, there's Graal, there's C2, and you build upon it, or you do everything on your own. Yeah, you will have more design choices and you will probably have fun doing it.
Yeah.
But it's like literally many-year efforts. Like,
you got some doing to do. Absolutely.
Yeah. So in my opinion, today LLVM is a solid choice. It has some serious trade-offs, especially compile time.
Yeah, I don't want to pick LLVM for compile time, but otherwise it's pretty solid. Okay, fine.
Yeah.
Yes, actually, I have like some experience on LLVM. So when we decide to build up a shader compiler for GPU, and I grabbed a front end shader compiler front end from Mesa 3D project. And then I got like a IR translator from Mesa 3D's IR to the LLVM IR. And like in 1 year, I got like a runnable shader compiler. So time to market is just 1 year. I believe that was a smart choice because we got the demo. We got a demo in just 1 year. And so this is not impossible if we build up a new compiler from scratch.
Well, I don't say not possible. Just
for me.
Yeah, fine. In your situation, this was a better choice. I might be coming from a different position.
Yeah, but back to my question is like I'm in doubt about this kind of thing because to pursue the like extreme performance, maybe I should choose like build up everything from the scratch. But I feel that the thing isn't like you write code on your own, which might introduce new bugs. The thing is we need to understand the problem and design choose like a smarter optimization passes and get a decent job. And especially you are talking about runtime support. So I feel that runtime support has nothing to do with the LLVM infrastructure, right? Because you have to build up everything from the scratch on your own.
The point is the lack of a runtime gives a lack of information to LLVM. Also, it makes LLVM make choices that you might do something else differently if you had a freely code patchable situation. So it goes back and forth, but the end result is some interesting amount of performance is being left on the table because there's not a runtime going hand in hand with LLVM.
Do you have an opinion on carrying runtime information from one run to the next? So like Python has the PYC files and saves some of the stuff that it's already parsed and generated code for. I could imagine something like LLVM essentially saving all the performance counters so that when you start it the next time, it assumes it's in roughly the same state as it died in last time.
Yeah. If I had to go make LLVM take performance data and I didn't want to build a runtime, first thing you do is you just profile it once, throw it in a file, hand it to LLVM next go around.
We actually do this for Java.
Yeah.
We have a way to capture a profile from one run and then restart with this profile. And then this profile will continue evolving. You will discover new facts and you can again save it, and next restart will start with that last point.
So you like keep accumulating run to run.
Yeah.
Yeah, okay.
So you are saving profile data, but not saving JIT code.
We can save JIT code as well. It's not the default configuration. Like the user needs to turn things on. But yeah, we save the profile, we save the JIT code. It is organized as a cache, so it's not that we just take everything which was there and have 100% reused. Because let's say the profile changed, okay, we'll need to recompile the new version. But if in this run the profile is the same, everything is the same, it's possible that we can reuse what we compiled in the previous run.
So you use basically profile signature, if you will, to validate that the code generated is good quality. There's a separate correctness thing, like all the classes got loaded that you depended on, things like that. And they got loaded the same bytecodes. No one changed the bytecodes out from under you and the like.
Yeah, so the key in the cache is the initial non-optimized IR. So we do the parsing, and then we just see whether we had the same initial non-optimized IR in the cache.
Okay, oh, that's interesting. Okay, and then if you do, you go look in the cache now and skip the remaining steps.
For the binary, yeah.
Ah, that's cool. Okay. Yeah, I voted down caching the code 20 years ago because there were too many open, outstanding issues that hadn't been solved. But sounds like you got it figured out now. Sounds good to me.
Yeah, we had very nice separation of compiler inputs. We can actually dump them in as textual files and do offline replace of compilations. And well, if we can save them for offline recompilation, we can also use them as key for the cache. And it is guaranteed to capture everything which is required for the compilation. So it kind of solves the correctness issues.
Well,
And potentially
okay.
you could plumb that data back. Have your IDE actually highlight lines of code and be like, here's the things that your in production runtimes think are hot. Please spend your energy there.
There is a cool hack that actually I did it to Azul. I think Azul still has it, where we exported the profile data to a browser of a live running JVM. Like Hotspot's continuously profiling at a low cost, low level, but that data is not typically available, except we made it available on the browser, and you could sort through and stare at your live running program and see what up and down, like surfing the heap and doing all kinds of fun debugging like things.
Yeah,
Is there a
Java
link
has
for that
something.
or a keyword?
On an Azul VM, ask Arthur. On Azul VM, there's some flag you throw, and it becomes a URL.
I'm not sure that we still have it.
Zing? You don't have Zing?
I mean, in the profile dumped as a HTML file. That does not sound familiar.
Wow, that would be really. I would totally go that route again in a heartbeat. As a compiler engineer, diagnosing your broken compiler, and as a high performance dev, diagnosing why my code is slow, being able to throw up the machine code that got JITted with hot performance counters and the Java code hung off to the side, this was like an amazing tool of your live.
Wait, okay. Got it. I thought you were talking about profile collected by like C1 or interpreter, and you're talking about assembly annotated with.
I looked at all the profiles.
Okay.
So we looked at the C1 profile data. Yeah, I could dump the C1 profile data, the C2 profile data, but the machine code with the annotations, everything. All of that
Okay,
stuff.
yeah. This thing is called ZVision.
Okay, so but it's still there. Yeah. Okay. Yeah. This was a stupidly obvious thing that I did while I was at Sun, and the Sun higher up said no, and we kept it internally because it was too fucking amazing. And when I walked over to Azul, I said, "Hey, do this amazing thing," and here it was. And then Gil got a hold of it and made it hard to use for devs. It's like really stupid. Oh, we're gonna make a server product. I was like, oh god, never again. I'm not going to lose control over my cool open source shit again that way.
Oh, is this feature similar to the replay file of Hotspot?
It's not a replay at all. This is live profile data.
I think Zin is asking about replay compilations, which I talked about.
Yeah, because the replay file also contains of the kind of like metadata information. So make sure that you can reproduce the compiler bugs.
So I know that Hotspot and C2 gained this ability. It wasn't there from the beginning, but they introduced it at some time. I don't know how well it works. So I don't know how it's structured.
Yeah,
but in spirit, it's similar. Yeah.
Yeah, because replay file has some kind of compiler instruction, compiler directive tell you to tell that Hotspot to compile this method or not. And on the other side, because C2 is a speculative compiler, so you have to to trigger the problem, you have to make sure that the method data or the profiler information is exactly same when you last time you saw this kind of bug. So that's why replay file also contain some kind of metadata or profiling information.
We were using the replay file as a debug tool back at Sundays. We made the replay file to help us debug these things.
This is about the amazing tools you mentioned back to the sun.
Although, what does it capture? So do you still need to restart the VM and it will replicate the...
Yeah, I'm in a debug session. I'm trying to debug my compiler. I'm running a large, complicated web server. It's the only place this bug shows up. It has 1,000 compiles that have to happen, or it takes too slow to get to the compile that crashes. So I needed to run a bazillion compiles. When I get to the target method, it needs to inline the following things and have enough profiles to trigger the following optimizations around whatever. And I don't know what all those are.
I understand the problem really well. I'm just curious how how is it solved with this replay mechanism?
I thought it, I don't know. I'm trying to think if I did it at Azul. I thought I did it. And it was definitely came from Sun. I thought I had Azul. It was just a text file. It had a list of methods and inlines. And you asked it, I don't know that it did them in order. It just decided the inlining. So it had some profile data buried in it too, though. And shit. Okay, Zen, sorry, you go. I don't know. I haven't touched it in a long time. There was just you read a text file on the start of the VM. You threw a flag. Here's a reprofile thing.
Well, I guess, and that's what I vaguely remember. I think you still need to restart the VM, but
Yeah.
you have a file which tells which compilations in which order and with which parameters to redo.
Yes.
Right. The goal was to replay in the debugger over and over and over again until you got it right. There was no hot swap or anything, or pop frame. I'm talking about a C compiler, a C, GDB running a C program that was hacking the stack and every possible ugly thing you could do, and replay. Okay, the closest replay we had was rerun the entire program from scratch until the JIT kicked in with the appropriate inlining arguments. Due to vagaries of scheduling and to vagaries in therefore performance counters, you wouldn't get the same compile at the same time, so you could never track the bug. So we had a bunch of tools to help you track compilations so you could debug it. One of them was the replay file. One of them was CI start stop and binary search over compilations that were broken. Several techniques were only stopped in the debugger on this kind of a compile.
The replay we have where we capture all the inputs and then can do the offline replay. One of the coolest thing in terms of debuggability we have is we save the replay information in memory while the compilation is running. So if we have a core dump and let's say it crashed somewhere, if we have a core dump, we just extract the inputs for the compiler and we restart it offline, and it saves so much time.
That's really cool. I like that. Because the compiler is so separate, you've separated the compiler well enough.
Yeah, we have all the inputs.
Process.
We extract the inputs from the core dump, and then I can play with this compile as much as I want, without a VM, just running out from LLVM.
Yeah, that's really cool. I couldn't do that back in the day. We ran the whole VM from scratch, and then we got to where the compiler blew up, and you had to figure it out from there. Like I said, there were a lot of techniques we did to make that tractable, but occasionally none of them worked, and you went to the replay file. Replay file was not my first grab. Eventually, I had a stupid script that did CI start stop to exclude methods in an ever narrowing range of exclusions that was automated, like on the GitHub. Git has a binary search for the commit that broke you. Anyone remember the name of that thing?
Yes, I know that.
Bisect.
Blame?
I'm sorry?
Are you talking about blame?
Bisect.
Well, no, not blame. Bisect.
Halfway between.
Git bisect. Yeah, I had a thing like Git bisect that would pick the compilation that was failing. It was just a shell script that just ran back and forth and walked in exclusion zones until I exclude this method and you work. I run this method, you die.
Yeah, the replay and the core dump was replay. It works if it's a compiler crash, but if it is a miscompile, you still need to have all these tools like, okay, which method exactly produces bad results? Now you need to bisect.
Generated. Yep, was there plenty of times.
Arthur, what's the definition of compile? So what's the definition?
Well, your compiler didn't crash, it produced some code, but the code is incorrect. And now the program has incorrect behavior.
You mean your toolset can identify those kind of miscompilation, don't you?
That's not what he said.
Yeah, we the tooling we have works really well for compiler crashes. But if it is a miscompile when compiler didn't crash but produced something incorrect, well, it's the same like with
you dropped a read barrier. The garbage collector at some future GC cycle fails to walk something that's live, collects it, and then you crash when you access an object memory that got wiped by the GC.
Yeah, and it happens like once in 6 months. Good
And-
luck.
That,
Yes, and so yes, I also have this kind of situation, and I don't know. So sometimes I got a lot of crash reports about GC, but actually it's not because of GC. So I believe that's the miscompilation things you mentioned. So do we have like a solution for those kind of things?
that's what he's saying. No solution. Not so easily. Break it in the debugger. Start looking at the code. Execute the code you generated. Shit like
Well, in my experience, the best thing we can do about it is to assert invariants heavily.
yes.
Yes.
The GC one, the GC guys had a bazillion invariants you could throw in and nail it down a lot easier that way.
Yeah.
That was the blah, blah, blah lot flags. Blah, blah, blah flags are at OpenJDK.
I'm still wondering how can you build up this kind of complex optimizing compiler 20 years ago without like a G-test or some kind of unit test. So yes, we do have like a GT test to we verify different optimizations or different parts of compiler using Java, but some kind of fundamental data structures.
Cliff had make.
I did make, yeah, exactly.
Make, everything can be done in make.
And Emacs, don't forget Emacs.
Emacs and make, and you're there.
Yes. No, I made heavy use of GDB, GCC.
Yeah, the thing is, when I modify C2 codes, I really want to, write some kind of Google test to verify that this part of code, do some kind of unit test to verify this part of code. But the thing is, it's non-trivial because C2
I know.
only works in the compiler thread. There are like many preconditions, prerequisites of this one. It's not very easy to build up a fixture, test a fixture.
I do that now. I didn't 20 years ago, but today I would do that. Yes.
But
Yeah.
LLVM has like a better situation because LLVM have a lot of infrastructure.
LLVM is unrelated. LLVM has a narrow problem domain. It's only generating code from a fixed set of inputs.
Yes.
Well, but you can argue that any compiler in hotspot also has the same narrow like.
Yes, exactly.
problem statement.
Exactly.
And you can't
The
test them.
compiler alone is debuggable using standard debugger compiler technologies. The combo of the runtime, the running, and the JIT code has a new set of problems and all the old ones as well. And the new problems need new solutions that no one had to harness for a cool idea 20 years ago. And now their cool ideas are floating around. But 20 years ago, you winged it every time.
Yeah, and it's impressive how like it is a really complex piece of technology, and it has evolved for 20 years. And the I would say unit test coverage is not that great. It's like almost not there.
It's protected by
compiler?
its complexity because a lot of people won't touch the code. It's too complex for them.
Yeah, there's an active OpenJDK section. It's fine. The way that the compiler gets tested, what you're talking about, Zen, is we typically run a bunch of stress tests that target the compiler. So XComp and varieties of XComp-like things will go tease out small, simple test cases where things are just broken straight up, and then they're sort of relatively easy to diagnose and debug. If you had a misgenerated code, it depends on how the misgenerated manifests. Sometimes it looks like a GC bug, and then you go at it from the GC cycle, and eventually you can sort out that between here and here in the timeline, something broke, and the GC people are complaining about missing something. And also the JIT was kicking in, and the JIT was doing something. And if I exclude this method, the GC people don't complain, and back and forth. So there's a ways to do it, but it wasn't easy, and it took a while to get there. There's a fun social thing, by the way. When I joined, there was the new JIT was the old new GC was now what's called the old collector, the old parallel collector, prior to having young gen parallels, I mean old gen parallel collector. It had bugs. All new bugs looked like GC bugs. This was the state of affairs that they, and long past the point when there were GC bugs. There were bugs in the runtime, there were your race conditions here, there whatever. My JIT showed up and it did fantastic things on benchmarks and it had bugs. And then, pretty quickly within a month, all new bugs were figured to be JIT bugs. And for about 6 months, they were right. But then the JIT got more and more stable and fewer bugs were JIT bugs. And I got blamed, or the compile team got blamed for all kinds of bugs that have nothing to do with the JIT every time for a long time, until the next generation of GC showed up at the C1 or whatever hell it was, G1, and not even G1, pre-G1, whatever, CMS, whatever. Something showed up to train. There were a bunch of them in a row. And suddenly all bugs were those guys' bugs. And the blame target, the pinata for getting beat on, bounced between the runtime, the garbage collector, and the compiler according to which version of which JIT was the latest cool thing to show up. And for about 3 months, they were correct. And for about 6 months afterwards, it was inappropriately blamed. And it got really old when you got told that there's some horrible JIT bug and it's blatantly a GC bug. And like, oh, Jesus, guys. Fine.
Yeah, another great way to test compilers is fuzzing. Like we has been running fuzzer for a couple of years, and it's just like you have some non-trivial change. You just ask QA to run fuzzer on your build for a while, and it finds problems.
How often do you run fuzzing? Do you run it after each commit, or do you run it nightly or weekly?
I think it's run on nightlies. So it's not okay. We have a corpus of fuzzer generated tests which run on every commit, but we also have an ongoing process of just generating tests and running them, and this is run on nightly builds.
And how long do you keep each fuzzer run? Do you run it overnight and then you stop after you have a new commit, or do you just keep running?
There is some process, like if there were fuzzer tests which found issues before, they get collected into the corpus, and I think we keep generating new tests in general and run on new builds. So I'm not very certain about the process, but there is some process around how we select the tests.
Okay, yeah, that's something I'm interested in.
Yeah, it sounds like a reasonable.
Also, one thing, like it's a good thing. Okay, you found a new bug which was not caught by existing testing of fuzzing. Well, you just go and introduce a new construct to the fuzzer and make sure that the fuzzer could generate the problematic test case for the non-fixed version.
There's also this interesting use of fuzzers to discover optimization opportunities. If you can set your criterion to be some metric of performance, sometimes performance counter, possibly cost model on the level of the IR, you may be able to discover optimization opportunities for local vectorization.
I hope that fuzzer generated code is not a good model for code in the wild, but I'm not sure.
I was just going to say that.
I was actually thinking about something similar. So one thing I was considering is, let's say we have some benchmarks, and if we can fuzz modify them, and if we have modifications which semantic preserving, like kind of refactoring.
Yeah, just you are answering pretty much, but I will just make this point also. It's all about the corpus. So if you start with the benchmark, just as you said, you are going to probably generate something very close to the existing benchmarks you are compared on, and thus representative for how the market values you. It's all about the corpus.
And if there is some like refactoring or modification which breaks your performance, okay, go look at that, because that's strange. It's the same semantics, but phrased differently, and your optimizer doesn't handle it for some reason.
Yeah, there have also been some differential testing methods discovering the loop optimization opportunities between LLVM and GCC. And that was pretty much done by methods very similar to fuzzing.
I have a very funnily similar, eerily similar, different take here. I'm doing this typing in GraphIR, which is aggressive rewriting as I go. So aggressive rewriting is basically C2 doing people optimizations while it's doing type discovery. Fine. In order to guarantee that I type things the same way every time, I guarantee a fixed point in all optimizations done to the graph. So I validate that I'm getting every possible optimization every time. with a pretty nasty, heavily aggressive assert. But I have a bunch of issues that show up then in terms of missed an optimization opportunity, or somebody who can now make forward progress didn't get on the work list or whatever. The incrementality of it and the got it all kinds of behaviors require aggressive testing to track. It's kind of a subset of what you're at, but I am able to take sort of any given program and visit it in any given order, any random order, and guarantee the same set of transforms ultimately show up at the end. So I'm headed for the one-step church roster property. I don't know if that makes any sense to anybody, but that's the piece of it. But the similarity here is that I would say that if you handed me any program which had the same semantic meaning modulo modest syntactic changes as you would get out of a fuzzer, I will 100% guarantee you I'll get the same answer every time, because if I don't, I have failed my typing to produce type the program the same way.
One engineering issue is that I'm also curious about is prioritization, and this is both in the case of crashes, but also in terms of optimization. So if you that's the problem raised already above. If your fuzzer input is not representative of the code in the wild, and you have a tons of crashes, then one could say, who cares?
No.
So how do you prioritize the crashes that are the closest to the crashes that are going to be encountered in the wild among thousands of?
I always claim that you have to get the crashes before you get to performance, because otherwise your language has a
absolutely. But how do you prioritize crashes if we go to we go to the bugs of any existing production compilers? You always have tens of thousands.
Slow down. So there's an easy answer here. It's the easiest ones to track down and debug. Go first. Which
among tens of thousands, again, how do you select the ones that you are going to
tens
rank first?
Tens of thousands. What?
Well, go to Bugzilla for GCC or to Bugzilla for LLVM and count the open bugs. I don't think OpenJDK does much better.
So if I look at what I saw as compiler bugs out of fuzzer-like tools, which I've totally done, there would be in the beginning thousands to tens of thousands, of which 99% were highly identical. So you went down the easy ones for a while, then you went down the high count ones because they were all similar and it would clean out your bug queue. And I never ended up with a bug tail distribution like what you're saying, where there's an actual crashing behavior out of the compiler that lived for like 5 years or never got sorted or whatever. Those all got cleared out.
Do you have some automated method to sort by similarity? Because that's actually a good point. You have a lot of duplication.
Usually you look at the stack trace where the crash came.
Stack trace. Yeah, that's reasonable. Yeah.
I crashed here again in the in the bit vector alias analysis step 5, whatever. I took some crash there. Okay. I get 500
okay, I like the stack trace idea even for automation. Now, switching the context slightly, now suppose that you are using fuzzer for performance differential discovery of missing optimization opportunities. Could you prioritize it similarly? You may be able to look at the stack trace of optimization passes that have or have not run.
No.
But when they give an output, no.
I only ever take somebody's exciting code and believe that that's the reason I want to go forward. And as soon as I see the why and I believe the commonality, the marketplace for this optimization is broad enough, then I make a poster child test case where the compiler fails to get it right, and it should, and then I go test-driven development, use my poster child till it works, and then we go back to the benchmarking side of things and see how performance goes. I never use fuzzer-generated things for benchmarking.
I think with optimizations, you can come up with so many. You can come up with so many corner cases which you can improve by some heroic efforts. Mm-hmm. But then there's always a question like, how common is this?
Who cares?
Is this one single method in your whole like test base, and this method is not even hot? And yeah, we have some kind of ways to we have a way to collect metrics on how often some patterns show up. And if you are thinking of some optimization, well, add the pattern to this thing and see how often it occurs on the corpus of tests you have. And if it like 5 times for hundreds of tests, well, probably not worth your time. But if it's hundreds, thousands, well, it might be a good
Exactly. You have to have some way to distinguish. You have an infinite set of optimizations to do. Have to have a way to distinguish them. All right, folks. We're an hour and 40 minutes, thereabouts. Zen, I claim that paper is no good, but I'll let other people make their own judgment. If people want to talk about this paper next go around, we can. I read it briefly. It made a lot of, in my opinion, factual errors and missed the obvious counterexamples in a big way. I think the paper's full shit.
Yeah,
But, I'm happy to back it up, but not at an hour and 40 minutes in.
yeah. The thing is, you just mentioned that there are like thousands of rewrite rules in C2, right?
Well,
But,
you're hacking it. How many do you think there are?
yeah,
It's not thousands. It's probably hundreds. But
let's say that there are hundreds of rules, but
yeah.
they scatter different places, and I feel that it's attractive to have like a DSL, domain specific language, to describe them and compile them into like C or C++ code.
Right. I tried several times. Let's have that discussion next week. I totally tried to do this pattern thing you're talking about several times with all kind of cleanup things. The closest I ever got was the toolbox of things that show up in the parser for doing some stuff there, but I never got it. I never got a pattern match rewrite rule that was generic enough, that didn't require every kind of exception on the planet, that was less work than just writing a piece of C code to do all the filtering. 99% of the time, it's all filtering out things that you can't take it from and being efficient about the filtering. And then 1% is the actual rewrite. It's all about filtering first. And like I said, I never got that. So let's have it next go around.
Yeah, but the thing is, I had the experience like the C2's rewrite rules and the LLVM's instruction combiner. So I had a similar feeling, I have the similar feeling that, even though we try so hard to iterate so many rewrite rules, right? But we cannot guarantee that our repository of rules are exhausted.
Zen, this is not a short conversation. Let's take it next week.
Okay.
Thank you.
Yeah, sure.
But I am happy to take it. But
yeah, I agree. That's interesting.
Okay. We've got 2. Actually, I'll vote in on anyhow. So that's 3.
We could totally spend an entire week on it is a moving target, and when the entire world suddenly decides to change how they write code and make everything change the futures, you need to change your optimizations.
Yep. Okay. Next week, folks. Sounds good.
Cool. Thank you.
Yeah.